around 45 minutes. Your PhD intituled Learning Effective Video Representation for Action Recognition. And after we will have this Q&A session with all the members of the jury. And traditionally, we start with the reviewer and after the examiner. Okay, thank you.
Okay. Okay, thank you, President. Okay, so I will start now. Good morning, everyone. I'm Di Yang, and I'm glad to present my thesis titled Learning Effective Video Representations for Action Recognition. I'd like to express my gratitude to all the jury members for their time and considerations in evaluating my work. In today's presentation, I will start with an introduction to the research area, followed by a detailed discussion of my three main contributions during this thesis. And finally, I will conclude with their impact and future directions. So now let's begin with the introduction. This thesis focuses on human-centric action recognition. Human-centric action recognition in AI refers to the technology's ability to identify and understand human actions and behaviors in the video content. The goal is to enable AI systems to recognize and respond to human activities in a way that's useful for applications in real world. For example, the smart home care monitoring, health monitoring, sports analysis, and other important applications like security and robotics. However, current action recognition approaches are still limited in performance when applied to many real-world challenges. For example, like cluttered background scenes and large variations of viewpoints and subject appearance, and to deal with the complex compositional activity that performed at the same time in the same video. And other important challenges. Our insight is that for action recognition, it requires effective and generic video representations. So this thesis will focus on learning effective video representations for action recognition. So what is video representation? Here is a general pipeline for action recognition. Firstly, we input a video sequence to a video encoder, and this video encoder can represent the video in a low-dimensional vector. We call it video representation, which extracts the features related to the human action. And then the video representation is fed into a classifier for two our main focus tasks. The first is action classification, where only one action will be performed in the video clip. And another important task is frame-wise action segmentation. This is a multi-label per frame action classification task. It means many compositional actions can be performed at the same time and even at each frame. So here we can see the video representation is very important. If we can learn effective video representation, and it can be helpful to beneficial different downstream tasks, including any other video based tasks like action anticipation and video retrieval, etc. And how to learn video representation? Here we think that video representation learning is a pre-training stage prior to action classification and segmentation tasks. We firstly pre-train an action recognition model based on a large-scale data in a self-supervised manner, and then we can get a generic model that can extract effective video representations, and then we can transfer this model to our specific downstream tasks like action segmentations on the home care monitoring dataset. So there are three main key problems for this representation learning stage: the data, the pre-training data, and the generic model. And the third one is how to train this generic model using self-supervised pre-text task. So in this thesis, we firstly focuses on skeleton-based action representation. As skeleton data has advantages like robustness to the noise caused by background clutter, changing light conditions, and the model can focus on the action being performed. So it generally performs better for many motion-focused scenarios. However, when I started PhD, we did not have a very generic skeleton-based model for that is very well self-supervisedly pre-trained and can transfer to any downstream tasks. There are three main issues. The first is data. There are many open source video datasets, and we can collect video not very easily, but we don't have the skeleton annotations in these videos. So it's based on the pose estimation systems. And the second issue is that we don't have a very generic model that can unifiedly process the skeleton sequence for action recognition. And the third issue is we have to design a self-supervised pre-text task for learning such model. So in the first two contributions in my thesis, I will focus on the skeleton-based action representation. For the contribution one, I firstly improve the pose estimator to get higher quality skeleton data directly on the real world videos without using action annotations. And we also propose a unified skeleton modeling to process skeleton data for action recognition. And for the contribution two, this work is to improve skeleton representation generalizability using generated data. And in parallel, we also explore how to get effective representation for RGB videos. And for RGB videos, we mainly focus on the third issue, self-supervised pre-training task for more fine-grained downstream tasks. So the contribution three focuses on RGB-based video representation learning, and we improve the contrastive learning. Now, I present the details of each contribution of the thesis. The first contribution is a unified framework for skeleton-based action recognition. This contribution contains two parts. The first is SST8 PRS. It's a pose refinement system. This system aims at improving the pose estimations in real-world videos to get higher quality skeleton data. So the main idea is that we use multiple expert pose estimators from state-of-the-art to extract poses on top of a video frame. And we can see that we use LCRnet, OpenPose, and AlphaPose. And each of them has their advantages and disadvantages. So here we propose a novel selective spatial temporal aggregation mechanism, which can automatically select which joint is most probably be the correct joint by joint. And after this aggregation, we provide a confidence matrix score that is to estimate the quality of the estimated poses. It means that if the confidence score is very low, the estimated poses probably is not that good. So we check the estimated poses using this score and the threshold, and we discard the skeleton with a lower confidence. And then the preserved skeletons, the poses will be used for retraining the pose estimator, LCRnet. And here, we demonstrate the results. We use LCRnet++, and before retraining, we cannot get a very promising result in these challenging cases like occlusion and truncation of the body. But after pre-training using the aggregated poses, we can get higher quality results. And then we use this proposed post-refinement approach to estimate poses on a large-scale video dataset kinetics to create a skeleton-based pre-training dataset to support our research. So we call this collected dataset positics. The positics dataset contains 142,000 real-world videos with their corresponding 2D and 3D skeletons. All the frames are filtered from kinetics for hundreds to ensure that at least one person is detected. And subsequently, with this created dataset, we can explore how to learn skeleton-based action representation. So the second part of this contribution, we proposed a unified skeleton model that processes skeleton sequence to recognize the human action. Let's see how the previous work modeled the skeleton sequence. The previous state-of-the-art adopt graph convolutional networks, GCNs, to process the skeleton. They model the skeleton as a graph, and they perform graph convolution on each node from their neighbors according to the connectivity of the body joints according to the human natural topology. So here we should construct an adjacency matrix to represent the relationships between every joint. So for different data sets, maybe the skeleton data, the joint distributions and topological structure are different. So we have to predefine different adjacency matrix for different data sets. And this adjacency matrix is a square, and the value in it represents the connectivity, if the two joints are connectivity or not. And this is a normalized adjacency matrix. And how to use this adjacency matrix, the general pipeline to process skeleton model is like we firstly, the input skeleton sequence is modeled into a matrix, a three-dimensional matrix in C channels cross T frames cross V joints. And the channel means the channel is 2 if we use 2D pose, and the channel is 3 if we use 3D pose. It depends on the data set. And then the modeled skeleton sequence matrix will be fed into a graph convolutional layer for the spatial processing in the previous state-of-the-art. So we can multiply the input matrix by the previous adjacency matrix to implement the graph convolution. And we can get the output of the spatial processing. But there are limitations of using adjacency matrix and the human topology, because this representation may not generalize to action. Because, for example, when we drink water, we should consider the connectivity between the hand and the head. But this connectivity is not exist in the previous human topology. And it is difficult to transfer across datasets using different human structures. So here we improve this method by using unique. So for unique, the difference is that firstly, we adopt a multi-head attention mechanism. We have multiple stage, and we will calculate the sum at the end stage for all the head, and each head have the same process. And another important difference is that we don't make Fe multiplied by the adjacency matrix. We replace the adjacency matrix into a W plus A. The W is a dependency matrix here. So it is not initialized with a human topology. It's initialized with a uniform distribution, and the values are directly dense distributed to optimizing the learning procedure. And here we have a attention map according to the input skeleton data. So here is the general self attention mechanism, the A. And then we can get the output of this spatial processing. And we have the advantages is that it's generalized better across the data sets, and it generalizes better for the actions which are not only considered on the human topology. And this output will fed into a temporal processing. So for the temporal processing, we just use a very simple temporal convolutional layers, TCN, with related dilations. So we can get the output after several spatial and temporal processings. And this output matrix will be stacked by a classifier, and we can classify what action it is. And our our whole network is trained end-to-end using a cross-entropy classification loss. Because our dependency matrix is learnable, so we can visualize the matrix before and after learning to see how the human topology, the human joint connectivity is learned during training. And here we can see that from the early stage to after training, the dependency matrix goes from dense to sparse and salient. The dependencies converge to a sparse representation, and the salient values in red circles represent the dependencies that correspond to the action. And we also conduct quantitative evaluation comparing with previous GCN-based method on Toyota Smart Home dataset, which focuses on the old people human daily living activities, and the generally used NTU RGB plus D dataset. And we can see that the human topology is not the optimal way to learn the connectivities between human joints. And our proposed dependency matrix outperform the previous GCN-based framework. And to demonstrate the generalizability of unique and the impact of pre-training on our proposed POSITIX datasets, we conduct we conduct transfer learning. We pre-train the model on POSITIX dataset, and then we transfer the model for downstream smaller dataset, including Toyota Smart Home, Pan Action, and NTU. And our result confirms pre-training on POSITIX improves state-of-the-art methods when transferred and fine-tuned on all 4 evaluated datasets. And our unique had the best generalization ability. And here we also visualize the training curve for the accuracy with training epochs during fine-tuning. From the curves, we deduce that at the beginning of training steps, the pre-training had a significant boost, especially for smaller datasets. Because X is the training iterations and the Y is the accuracy. So the main difference is at the beginning, the pre-training can help a lot for transfer learning. And here is an inference demo on Toyota Smart Home. It shows that our method shows that if we use previous method, it will misunderstand the activity. It will think the lady is reading book, but actually the lady is using tablet. And using our model unique, we can better classify the class. Hence, in this work, we have proposed a novel human skeleton refinement method to extract poses on real-world videos. And then we proposed a generalized skeleton modeling, including a novel topology-free design strategy, and we use multi-head attention to learn the human dependencies using the provided topology-free dependency matrix. So here we want to further ask a question: how to train our unique in a self-supervised manner for further improve the skeleton representations. So the second contribution will answer this question. We propose a skeleton action generation and representation learning. To further improve the representation ability of unique, we target more challenging tasks like recognizing compositional activities and cross-view activities in the real-world videos. And our proposed latent action composition is a self-supervised framework aiming at learning from generated compositional actions for skeleton-based representation to address the issue 4 and issue 5. The general pipeline of LAC includes 3 steps. Firstly, we enhance the data through action generation. This is achieved by the motion and static feature disentanglement, and we can generate a compositional skeleton sequence, which combine the 2 single sequences. And then this generated skeleton sequence will be used for self-supervised contrast learning to improve the generalizability of our previously proposed unique model. And we can get a generalized unique. And finally, we can transfer this generalized unique to downstream specific action classification and multi-label action frame-wise classification and segmentation or cross-view action recognition. So the first is the generative model. How to generate compositional actions using the single action. Our insight is that each action can be decomposed into 2 parts. The first is the motion parts, which represents the temporal dynamics of each human joint. And the second part is the static part, which represents the viewpoint, the body size, this static information that are not changeable in a long time. And the motion information could be further decomposed into several basic primitive motions. So here we construct a learnable dictionary, DV, which is an orthogonal basis. And it contains 2 sets of directions. The first set of directions is the static, is the motion feature, is a dynamic motion feature. We call it DM. And the second set is the static feature called DC. And each direction corresponds to a basic primitive motion. It's like a decomposed primitive motion. And the static part represents the body size and the viewpoint, which is static. And we can see that each action can be considered as a linear combination of the orthogonal basis along their directions and their associated magnitude. And the magnitude will represent the amplitude of the basic primitive motion. So for training the generative model and the action dictionary DV, LAC is firstly input. We can input multiple skeleton sequences in skeleton encoder. And then we can get the features of skeleton sequence. And then we can compute the magnitude along the action dictionary, along each directions. And we can get the static magnitude of the static magnitude and the dynamic motion magnitude for the blue people. And we can also get the static magnitude and motion magnitude for the red people. For training, we will swap the static magnitude of these two people, and we can get a new feature. And then with this new feature and the generator decoder, we can generate the multi-view skeleton sequences, the cross-view skeleton sequences. We can see that the blue people is performing the action of the red people because we swap the static information of this pair. This is for training, and we have the ground truth for compute the construction loss because we use a synthetic data set having 3D pose, so we can rotate to construct the ground truth for training. And for inference after training, our goal is to generate compositional activities so we can combine the motion magnitude of these two people. We can get a combined magnitude of these red people and these blue people, and we can generate new people that performing two actions. And after this generation model, we can compose every two real-world videos for skeleton sequences. And we will conduct a contrastive learning in a self-supervised manner on top of these synthetic generated compositional activities. And for contrastive learning, we take the same action, same compositional action, but performed in different viewpoints as the positive samples. It means that we will encourage the similarity of the same action, but in different viewpoints to make the model robustness to view changes. And the contrastive learning is conducted in both video space and the frame space to make the to better generalize to frame-wise specific tasks. And the third step, as we generalize unique using the compositional activities, so this model can be better applied for the compositional, which is multi-label action classification tasks using binary cross-entropy loss. And as our generalized unique is also trained using view invariant contrastive learning, so it can be robustness to view variance. So our model can also be evaluated for cross-view action recognition tasks. So here we conduct experiments to evaluate our luck using the pre-training on positives in a self-supervised manner. And then we transfer this pre-trained unique model on more challenging tasks for action segmentation. We use Toyota Smart Home untrimmed version, Charad, and PKU-MMD to evaluate our model because such data sets has multi-label action classification challenge and the cross-view action classification challenge. And we use event level IOU and frame level average processing MAP to evaluate our quantitative results. And we use linear evaluation, self-supervised pre-training on positives. Linear evaluation means after the self-supervised representation learning, we freeze the pre-trained encoder and just retrain the classifier using action labels to evaluate the learned representations. And we can see that for this downstream multi-label segmentation tasks, the pre-training has a significant boost. And we also compare with other state-of-the-art on the same data sets using either RGB or skeleton data. And we can see that using the compositional activities and the pre-training, our generalized unique can outperform previous state-of-the-art on the target data set. And here to demonstrate the motion features have been effectively learned, we firstly evaluate the generation quality of lag by conducting action composition. And we can generate the composable actions from 2 customer input videos. And here are the demos of cross-view action generation on a sports analysis dataset, Pan Action. This is to demonstrate that the motion features and the static features related to the view has effectively decomposed and disentangled. And for this work, we present lag, including a generative model. And we use a novel linear action decomposition mechanism to learn and combine the motions using an orthogonal basis. And then we apply contrastive learning to learn our previously proposed unique in a self-supervised manner to increase the generalizability for compositional activities and cross-view activities. And here we will ask another question. For RGB-based video, how to learn the motion-focused video representation for more fine-grained tasks? So the third contribution is focusing on RGB-based video representation, the time-aware action representation learning. So in this work, we focus on contrastive learning in RGB domain. We want to retrain the video-based encoder to extract RGB features using action without using action labels by contrastive learning. So here is the way that previous state-of-the-art contrastive learning solved this problem. They randomly select different temporal segments from a video clip as a more positive views of one video clip, and then they maximize the similarity. They maximize the similarity between the different temporal segments in order to enforce the feature representations, enforce their persistence over time. However, for downstream tasks involving temporal relationships, a representation invariant to temporal shifts might omit valuable informations. For example, in differentiating actions such as enter and leave, the temporal order is fundamental. But if we train the network using the previous contrastive learning, the model will omit the important time information. So here our solution is we propose a latent time navigation, LTN, to parameterize time on top of contrastive learning. So the main idea is we go based on the general contrastive learning pipeline. We have a video, we have an anchor video, and then we randomly spatial temporal crop the video into different spatial temporal segments as the positive keys. And the anchor video is, and the first video clip is the query Q. And his multiple positive views is key. And all the query and key clips will be fed into a visual encoder based on like 3D CNNs or other video-based model. Here we use ResNet 3D for extracting the RGB video features, and we can get the video representation FQ or F key for the key positive samples. And if we do classical contrastive learning, we will compute contrastive loss on top of F. But here we do not directly compute the contrastive loss on top of F. We firstly transform the F to F prime, and then conduct the contrastive learning on top of the F prime. So the F prime can be formulated as this equation. We encode the starting point of each temporal segment, because when we randomly select a temporal segment, we can generate the time shift between the generated segment from the beginning of this video. So we have a time shift, and we encode this time shift value together with the video feature into a time encoder using MLP. This encoder can be denoted as epsilon. And how we encode this time information on top of the features, we reused the idea of the previous contribution lag to decompose the features into a separate space. So here we also create the learnable orthogonal basis, DT, including different orthogonal directions, which represent a subspace of these video representations. And we will we expect to make the model partially similar with each other, with each positive pairs, because they have same static information because as object and the scene. But we also want them partially different from each other because they have temporal changes. So here we encode the time and the features into a set of magnitude A, and linearly combined A with the basis dt. And finally, we perform the general contrastive learning on top of the F prime, where the time information has been encoded. And finally, during contrastive learning, it will maximize the mutual information between the time parameterized representation F prime by using the contrastive loss. And we also discourage the similarity between every query clip and these negative pairs sampled from other videos in the dataset. The evaluation is conducted using kinetics 400 pre-training and transfer learning on Toyota Smart Home, our main focused fine-grained activity recognition dataset, and two general video understanding datasets, UCF and HMDB. And compared with previous self-supervised methods on video action recognition on Toyota Smart Home, as activities of Toyota Smart Home are with similar motion and high duration variance like leave and enter. So we can show that our proposed method in the linear evaluation setting outperform previous self-supervised method, and in the fine-tuning setting, it can also outperform previous state-of-the-art and outperform many supervised pre-training approach. So in conclusion, in this paper, we propose a novel latent time navigation to parameterize the time information used for generating data views on top of contrastive learning. And now I will conclude this thesis by providing a summary of contribution and by outlining future research directions that build on our current algorithms. So our first contribution is unique with the two novel algorithms. The first is a multi-expert post-refinement systems, and the second is a topology-free skeleton modeling to model skeleton sequence and use it to action recognition. And the second contribution is LAC. We propose a novel generative model to generate compositional and multi-view action by learning the motion and static features using orthogonal basis. And the third contribution is focused on RGB-based representation, and we propose a time parameterized contrastive learning for fine-grained task. And here is the publications during my PhD. And our proposed models have also been evaluated on many real-world applications in the factory, and our methods have also been submitted for a patent with Toyota. However, there are still many limitations in my current work. First, in the model architecture level, our unique model is still not that generalized to deal with the different number of joints. For now, the current solution is like we can convert the different number of joints into a constant number using interpolation or some manual pre-processing. And our model have to extract a long-term temporal features for untrimmed videos to recognize all the actions performed in a long video. And we have to process multi-people and human object interactions using combining both skeleton representation and RGB representation. And in the data level, multi-modal, if we want to generalize our model to more multimodal settings, we should generate more data, including all the modalities like skeleton, text, RGB, and audio, etc. And for the learning approach, we are aiming at designing more effective self-supervised video-based free-text tasks, or the cross-modal along motion, language, and RGB for the contrastive learning. And now we are in the current step. We want to learn more generic video representations for action recognition tasks. So we want to extend the unique to a foundation model that is pre-trained on a very large scale skeleton data set to generalize to fix all the skeleton-based tasks. And on the other hand, we want to combine the skeleton-based motion feature to RGB and language feature to make it more generalized to the real world. And we can implement the zero-shot evaluation on the real world if we have a generalized motion and language model. And if we can combine the motion skeleton model to the large language model, we can also do many future directions like text to motion generation, visual language understand, like motion to text, text to motion, or video captioning, or a very long-term dense video description using having the motion information and other environment information. As human action representation learning continues to evolve, there are many future research directions in video domains, such as ego-centric video understanding and robot learning. Overall, learning from video helps AI systems to understand human actions and the world around us, making the technology smarter and more useful in everyday life. Thank you all for your attention, and I'm looking forward to further questions and discussions. Thank you.
Okay. Thank you very much, Dion, for your very nice presentation. You are perfectly on time. So we are going to switch to the second part of this PhD